So for 3.5, exponential and logarithmic models. In other words, these equations that can be used to model these different situations. That means this section's going to have a fair number of word problems in it. Okay? So this is one where you're going to actually want to spend some time on it compared to some of the previous sections that I know some of you have worked oh so hard on. So these are your 5 main models that are exponential or logarithmic. You have exponential growth, exponential decay. Okay, you also have what's called a Gaussian model, a logistics growth model, and a logarithmic models. We've dealt with the exponentials and the logarithmics already. The Gaussian and the logistics, those are some real world situations that we run into. Okay, and this would also all be in the book as far as those formulas go. Now, the Gaussian one is your bell curve, z-score, that kind of stuff. So it's one used for stats a lot. Logistic models are used in biology a lot because it looks at growth patterns of species and the limitations they reach, okay? We'll look at that one as well. So, graphically, well, here's your exponential growth, exponential decay, along with the Gaussian, the normal bell curve. Logistics looks like this, where you have it's slow growth at the start, then it spikes up once it hits optimal conditions. Then as your population growth goes up, eventually you start hitting a limiting factor, either space or food supply or something along those lines. Okay? And then your 2 logarithmic models, just for natural log and common log. Okay? So, if I have this model, how would you set it up? Population of the city is given by that, where t sub 0 equals 2001. According to this model, when did the population reach 150,000? What would you do?
Plug in 150,000.
Plug in 150,000. Then? Yep, divide by the 95,300. So you get 1,500 over 953, just to simplify it a little bit. E to the 0.055 t. And honestly, I would leave these fractions as improper fractions. Don't give the decimals halfway through, otherwise you will hit rounding errors. Then what? ln on both sides. Cancels on the right, giving you 0.055 t. Then divide by 0.055 t. Go ahead and do that. What do you get? Anybody else? Yeah. 8.25. Then what would the actual answer be? 2009. Because if 0 is 2001, add 8.25, you get 2009. Okay, not too bad when they're models that we're really familiar with. Or when they give you blatant information like that. One like this is a little bit more challenging because this is looking at exponential growth of population of fruit flies. After 2 days, there are 125 fruit flies. After 4, there are 350. How many flies will there be after 6? Okay. Now the problem with this is, because it's exponential, I can't just set up a ratio or anything. I need to actually find the values. Okay. Now both of these are going to use the exponential growth. So y equals a times e to the bx is that general form of it. What would I need to do here? Yeah, put an x and y. You have 2 sets of x's and y though, right? So I'm actually going to set up the 2 different equations. One for each circumstance. 125 fruit flies is a times e to the b times 2 days. And 350. Now what am I going to want to do with those? What do you mean?
Like between the 2 equations so that they would both be constant?
So set them both equal to A, then you can set them equal to each other. That way it works, yep. Is there any other methods? You could actually solve for one and then substitute as well. Okay. The way I like the best, though, honestly, because it gets rid of stuff faster, is the elimination method. You can do elimination on this. The problem is, because it's not a normal quadratic or a normal linear statement, those you basically set them up so you have ax plus by equals c, and then subtract the two equations from each other, right? Here you can do the same type of thing, but because there's no addition or subtraction going on, you can actually do it with multiplication and division. So if I set up 350 equals ae to the 4b over 125, and I should have done that as two fractions, ae to the 2b. This statement would still have to be true because you're just dividing each side, right? So, what can I do with the, well, what do you notice happens immediately? Yeah, the a's cancel. So that eliminates one of your variables. I like it this way because you don't have to actually solve out for one thing and get something weird decimal. I can jump right to what it looks like. 350 over 125, what does that simplify to? Well, yeah, this will be e to the 2b because you subtract the exponents. But what is the 350 over 125? What does that fraction simplify to? 2.8. Since it's a terminating decimal, you could do 2.8. I'm going to leave it as 14/5 just for consistency's sake. Okay, so from here, what do I do to solve for b? ln, yep. ln of 14/5 is equal to 2b. Then what? Divide by 2. I'm actually going to cheat a little bit. I'm just going to write 1/2 since I don't have much room left on the page. Okay, so that's the b value. Now what do I need to do? I need to plug it in and get a. So I'm going to plug it back into one of these two equations. It does not matter which one. So if I do 350 is equal to a times, actually no, let's do it this way. Let's do the 125 because it's going to be a little bit easier. Does anybody see why it's going to be easier? Look at your exponent. Yeah, the 1/2 and the 2 are going to cancel. So I have 1/2 ln of 14/5 times 2. So immediately the 1/2 and the 2 simplify out. You're left with 125 equals ae to the ln of 14/5. Then what? Yeah, the e to the ln, what are you left with? 14/5. So I have 125 equals a times 14/5. How would I get rid of 14/5? Multiply by the reciprocal. So I'm going to have 5 over 14 times 125 equals a. And 5 times 125? Should know that one. 625. I'm going to leave it that way. That's 5 to the 4th over 2 times 7. Nothing's going to simplify. So I'm going to leave that as a. Now, I don't have any decimals yet. I don't have anything that's going off to a decimals, non-repeating, non-terminating. Everything's exact numbers. Okay? If at any time I were to round before this, you actually end up about, I mean, it's not much. It's 2 to 3 fruit flies off. But it is, depending on what you're doing, can be significant. So I try to wait till the last second. So then I'm going to write my equation with those in there. Y equals, and I'm going to leave them that way. 625 over 14, because that won't simplify at all, times e raised to the b times, where was I? 1/2 ln of 14/5. Oh, not b. Sorry, that is b. Put the x after it. Okay. Now I finally got an equation of the model to work with. Then what? Plug in 6 for x. So that you can just type in your calculator. What do you get? Anybody? Should be a nice number. 980. Yeah, because of all the, we didn't round anywhere. There's no weird decimals going on. It's just 980. Flies. Okay. The problem is, the rounding errors can make a difference. Okay. Doesn't really matter here, but if you're trying to land a satellite on an asteroid, those rounding errors can make it so you land in a shadow and the solar power on the thing doesn't work. Anybody remember that recently? No? Last year? But yeah, they were trying to land on a asteroid or was it a comet? I don't remember now.
I
think it was an asteroid. Yeah, I can't think what the name of it was, but they literally tried to land on it.
I thought they were trying to land on Halley's Comet.
No, Halley's Comet's not due back for quite a while.
I thought that's what it was.
No. It wasn't Halley's Comet. But anyway, so 980 flies for that one.
Yeah, you were in like the middle of the story.
No, that was the story. They literally landed it in the shadow of a cliff on the asteroid, so the sun wasn't able to hit it and power and provide electricity for it. So they got 1/10 of the data, not even that probably, that they wanted to get out of this thing. After spending millions and millions of dollars to get the thing there.
Was that NASA or?
Yeah, it was NASA. But that stuff's happened before. They've aimed it. You aim at a moon of Saturn that's that far away. If you're off 1/1000th of a degree, you're going right by it. So I like using that as an example because your rounding errors add up when you're talking about that magnitude of distance and things like that. 6 days, fruit flies, yeah, it's like 98.15 or something like that versus 980 or 981.5 or something versus 980 because you're only talking 6 days. If you're talking trying to spend months with this thing in the air, or not in the air, in the non-air, in the vacuum, it makes a difference. Estimate the age of a newly discovered fossil with the ratio of carbon-14 to carbon-12. Now, if you had a problem like this on the test, you're going to be given the formulas to work with. Okay, this formula is actually on page 258 of the textbook, and the formula for this ratio of carbon-14 to carbon-12 is R equals 1/10 to the 12th times e to the negative t over 8,223. Okay, so this kind of problem you're going to be given a lot of the pieces you need. Then, if they want you to find the ratio of carbon-14 to carbon-12, well, all I do is plug the values in. R is this 1/14, or the age, find the age. Then I'm just going to solve it. What would be your first step? Which would be the same as multiplying by 10 to the 12th. If I multiply by 10 to the 12th, I'm going to get what on the left side? 10 to the negative 2, which is 1/100. Because you get 10 to the 12th over 10 to the 14th, you get 10 to the second on the bottom, which is 1/100. Then what? ln both sides. Then I'd probably do something a little different. I'd multiply by negative to get rid of that at the same time. If you multiply by negative 8,223 times the natural log of 1/100, that should give you the age of the fossil. How old's the fossil? Since we're talking on this kind of time scale too, let's just round to the nearest year. What do you get?
30,000.
Say that again? 37,000? Did I miswrite something?
30, no, you put 8, yeah, no,
Yeah, 8223 is the right number. Just a second. This number should be bigger than that. Oops, and then I typed the wrong number in. 37,000. Oh, I'm sorry. I was looking at a different problem in my notes. Anyway, yeah, 37,000 what?
27,868.
Years, yep. Sorry, I was looking at the wrong page and I didn't realize it. Okay. Gaussian models. These are the ones that is your bell curve. Okay. Now, bell curve or normal curve for those in stats. Properties of it, your average value is going to be the one in the middle. It's that maximum value in the dead center. Okay. The x value is going to correspond to that maximum value of the y. The x value is that average, or is average value of the independent variable. Okay, that's usually the one that you're going to want, because the other number, essentially, if you're ending up doing a z value of it, which is what you're doing for this kind of stuff, is going to end up being some number smaller than 1. Okay, it's kind of percents, but not really. So if I look at this situation using that Gaussian model, last year the math scores for students in a particular math class roughly followed the normal distribution given by that. Where x is the math score, sketch the graph of this function and use it to estimate the average score in the class. Okay, so instead of sketching it, I'm going to do it on the calculator. If I go to graph this, go ahead and put this one in. Oops, yeah.
The x minus 74.
Yeah, x minus 74. It's really small. Then what would I want to make my window?
-30 or 30 to 110.
Yeah, they basically give you the x values. What would you want to make your y's? Now think about stats. If this is a normal curve, or if this is a z to z, say again. For the y, yeah, the x is probably going to be somewhere around 70-ish.
Is it 1?
Yeah, max I wouldn't go more than 1. Okay, so I'd go min. I would just start at 0 and go to 1, something along those lines, just to get a rough idea.
That's a pretty small curve.
Yeah, the problem is that ends up being extremely small. So if you want to, you could do that. I would also then just adjust it. I would change my max, instead of being 1, make it 1/10. And slowly, it'll graph it. So then your max is going to occur where? Go ahead and find it.
74.
Yeah. 74. Yeah, this is like 74 and it's like that 0399 number. So what then was my answer? Would .0399 make sense for a score in a math class?
No.
Hopefully not. So yeah, 74 is going to be your average score. Questions on that one? Okay. Logistic growth models. This is the one where organics usually follow this kind of pattern. So a lot of times you'll have initial rapid growth, and then it slowly declines as what's going on is not optimal anymore. Okay. So the classic example is if you have a bacteria that's in a petri dish. Okay, the amount of food in the petri dish is going to determine when it starts declining, how much is available. So you get this population curve that starts off as a slow growth, then spikes up, and then as the food runs out, kind of levels off to an optimal. And then plummets once there's nothing left. But for this then, it's also called a sigmoidal curve, or sigmoidal, I should say. Not used very often, but biology you will run into it. Mainly, the equation ends up looking like this. On a college campus of 7,500 students, one student returns from vacation with a contagious and long-lasting virus. The spread of the virus is modeled by that, where Y is the total number of students affected after T days. The college will cancel classes when 30% or more of the students are infected. Okay. So, how many students will be infected after 4 days? Go ahead and find it. How many?
36.4.
Yeah, so about 36 students or so. After how many days will the college cancel classes? What would I have to do for that?
Find 30%, 7,500.
Yeah, find 30% of 7,500 and do what?
Divide it.
You plug in for Y. This is complicated enough that I probably wouldn't bother. There's a few different techniques you can use to get through it a little faster. You can actually flip both sides of the equation over, and then multiply by 7,500, subtract 1, divide by 74.99. I'm going to do it a slightly different way. I'm actually going to graph this equation, and I'm going to graph 30% of 7,500. Okay? If I graph both those, now logically my window, well, I'm not going to go past about 30 days. I'd also go for Y, the population, from 0 to the 7,500. Okay? So what that allows me to do then is to look at that sigmoidal curve as well as where 30% of the population is. Now how could I find the population when they would actually cancel classes? Or after how many days the population will hit 30%? Yeah, the intersect of them. So they're literally second in calc, go to the intersect. First curve, second curve. Since they only cross once, guess. So in other words, after about how many days?
9.
Yeah, about 9 days. Questions so far? Okay. One more. The Richter scale is magnitude of earthquakes. So magnitude R where earthquakes of intensity I is given by R equals log of I over I sub 0. Where I sub 0 is equal to 1, that's the minimum intensity used for comparison. Okay, so it allows you to compare different earthquakes. Find the magnitude R of an earthquake with intensity of those. So in other words, this one's actually very, very simple. R is that magnitude of the quake. Is log base 10 of, well, I sub 0 is just 1, so I'm not even going to bother with it. So it's just whatever your I value is. So what's log of 68,400,000?
7.8.
7.8? Yeah, 7.8. I was just remembering 2 decimals before, but that's fine. For the other one, what do you get? 7.6. So if you actually think about when they, not too much around here obviously, but if they talk about the difference in earthquakes between a 7.6 earthquake and a 7.8 earthquake, doesn't really sound like that much. But if you look at the intensity of it, it's almost 150%. From 47 to 68. It's that many times as intense, 1.5 times. That's why when you look at from a magnitude 6 to a magnitude 7 is how much more powerful. 10 times as powerful. Okay. Questions on anything from 3.5? That's all she wrote.